What's up guys? This is Engineer Jack and this is reinforced concrete. So for our introduction in flexure and beams, reinforced concrete beams are non-homogeneous in that they are made of two different materials kasi nga they are made of steel and concrete. So the methods used in the analysis of reinforced concrete beams are therefore different from those used in the design or investigation of beams composed of entirely steel, wood, or any structural material. Kasi nga, yung naaralin natin dito is yung behavior of two different materials, yung combination of steel and concrete. Two different types of problems arise in the study of reinforced concrete. So yung una, the analysis, and pangalawa is the design. So kahit anong structural member made of reinforced concrete, for example, meron tayong beam, column, slab, or even foundation, or kahit anong structural member basta made of reinforced concrete, meron tayong dalawang problem lang yan. So meron tayong analysis and design. So sa analysis, yung given lang dyan, meron tayong given na dimensions, for example, of the beam, meron tayong width na B and height na H. So yung given din sa analysis, meron tayong FC prime, or ito yung compressive strength of concrete. So nakukuha natin yan dahil sa class mixture natin, kung anong klaseng pagkahalo niya, and given din yung Fy, or this is the yield strength of steel. So ito yung strength naman of our reinforcement steel. And syempre, sa analysis, given din yung diameter of bars. Ngayon, yung analysis naman, yung hinahanap natin dito, yung resistance or design strength of the member. Ano ba yung capacity ng member natin kung beam siya or column or any structural member? Because of this combination of concrete and steel and kung gaano karami yung bakal natin, i-compute lang natin kung ano yung design strength niya or capacity niya. So for Mn, this is the nominal moment capacity. Tapos pa nag-multiply tayo ng strength reduction factor or phi, yung tawag na sa kanya is design strength. Pag magde-design tayo ng beam, usually ginagamit natin is yung phi Mn and phi Vn. So yung phi Vn ginagamit yan sa pag-design ng stirrups. So dadaanan din natin yan dito sa reinforced concrete. And ito naman na phi Pn, ito naman ginagamit to design a column. So usually para sa bakal lang longitudinal bars of beams, yung ginagamit natin is phi Mn. And dapat it should be greater than or equal to Mu para sa phi Mn. And para naman sa phi Pn, that should be greater than or equal to Pu naman. And para sa phi Bn naman, that is also greater than or equal to din dapat sa Vu. So itong phi Mn, phi Pn, and phi Bn, ito yung strength provided natin. Ito yung dahil sa material natin, anong dimension natin, anong bakal na ginamit, diameter, ano yung Fc prime, Fy. So yan yung strength provided. And ito naman yung Mu, Pu, and Vu, yan naman yung strength required to carry factored load. So nakakompute natin yan using structural analysis. And gagamit tayo ng mga load factors. Kumbaga, minamagnify natin yung load. I-magnify natin siya using load factors. So, nakadepende yung load factors kung dead load siya or live load or depende kung anong klaseng load siya. Pero kung floor systems tayo, usually yung 1.2 or 1.6 lang ginagamit natin for dead load and live load. So, ito nakakompute lang due to loads and iminamagnify natin. Kaya ang tawag sa kanya is factored loads. And dapat yung strength provided natin is always greater than or equal to the strength required to carry the factored load. Siyempre, pag nag-less than yan, siyempre, mag-fail yung material natin or yung member natin. Kasi nga, yung strength provided natin, siyempre, siya lang yung magdadala. And kung less than, siyempre, masisira yung structure natin. Yun yung iniingatan natin. And for design naman, so this time, ito talaga yung real or tunay sa structural design. So yung given lang dito talaga, yung factor design moment, axial, and shear. Yung given is yung Mu or Pu or Vu, pero pag magde-design tayo ng beam, yung given lang is yung Mu. Yung required this time, ano ba yung dimensions of the beam? Ano ba yung width niya? Ano ba yung height niya? Ano ba yung gagamitin natin na Fc prime? Anong class mixture niya? Anong pagkakahalo? Ano ba yung Fy natin or the yield strength of steel? Kasi itong Fy, given na yan sa manufacturer. So, bibili lang tayo and may designated Fy na talaga yan. So, another requirement naman sa design is syempre, ano bang diameter na gagamitin natin? ano bang diameter of bars. So, meron tayong 10 millimeters, 12 millimeters, 16 millimeters, hanggang 72 millimeters of diameter of our bars. So, as you can see, para sa design, yung given lang is yung factored loads for moment, for axial, and for shear. Pero yung required, lahat, yan yung tunay na design sa real world or sa real structural design. We have also assumptions for strength design method. So, una, our strains in reinforcement and concrete are directly proportional to the distance from neutral axis. Ito yung neutral axis kung nasaan yung centroid of our cross-sectional area. So this implies that the variation of strains across a section is linear and unknown values can be computed from the unknown values of strain through a linear relationship. Pangalawa, the concrete sections are considered to have reached their flexural capacities when they develop strain in the extreme compression fiber. Kasi meron tayong dalawang fiber lang in our cross-section of beams, so meron tayong compression and tension lang na pinaliwanag din yan sa strength of materials. So number 3 assumption, the stress in reinforcement varies linearly with the strain up to the specified yield strength. The stress remains constant beyond this point as strength continues increasing. This implies that the strain hardening of steel is ignored. So itong number 3, mas papaliwanag ko yan kung na-visualize natin yung drawing and mamaya ipapakita ko yan. And number 4, laging neglected yung tensile strength of concrete kasi nga, yung range of our tensile strength of concrete, ano lang yan, from 10% to 15% of the compressive strength of concrete. So napakalit lang yung value of tensile strength. Kaya nga tayo naglalagay ng reinforcement kasi sila na magdadala ng tension forces para maiwasan natin yung cracks kasi nga mahina talaga yung concrete in tension. So very brittle yung concrete and ductile naman yung steel bars natin or steel reinforcement. And number 5 assumption, the compressive stress distribution of concrete can be represented by the corresponding stress-strain relationship of concrete. This stress distribution may be simplified by rectangular stress distribution as described later. So mamaya ipapakita ko yan. So ngayon, pag-usapan naman natin yung reinforced concrete beam behavior. So as the applied load is gradually increased from zero to failure of the beam or the ultimate condition, ito yung ultimate condition, ito yung failure of the beam may be expected to behave in the following manner. As you can see in the figure, itong behavior dahil ito sa mga laboratory test in our codes or the ACI, from the ACI yan. At uniform load or kukunti pa lang yung load na in-apply natin sa beam. So as you can see, meron tayong simple beam na merong hinge support and roller support. So, pag malit pa yung load natin na in-apply sa beam natin, so magkakaroon pa tayo ng section uncracked, so wala pa tayong cracks, and this reinforced na at the bottom. Yung behavior of strains natin and stresses, this is linear pa. So, itong stresses na triangular, so galing yan sa bending stress natin. So, for the stage 1, when the applied load is low or kukunti pa lang, the stress distribution is essentially linear over the depth of the section. Kasi nga, ganyan pa yung drawing niya for the strain and stress. So, linear pa yan. The tensile stresses in the concrete are low enough so that the entire cross-section remains uncracked and the stress distribution is as shown in the figure. So, in the compression zone, the concrete stresses are low enough. So, yung value niya is 0.5 FC prime approximately. And their distribution is approximately linear pa. So, kung babalikin natin guys, yung strength of materials, kung meron tayong simple beam, yung top area natin from the neutral axis or ito yung cross-sectional area of the beam, yung laging top section natin is always compression yan, pag simple beam. And sa bottom naman, always tension kasi nga andun yung malaking bending natin. Pero, kung indeterminate beam siya or meron tayong fixed supports or yung support natin in our beams is fixed, ibig sabihin, at the support section, babaliktad na to. So, yung top area natin magiging tension na and from the bottom naman, this compression naman kung malapit sa support. Pero kung sa mid-span, laging ganito yung behavior niya. So, yung compression sa top and tension sa bottom. Itong diagram na to, ito yung nakocompute natin from the strength of materials, this is the bending stress from the formula na M max times C all over the transformed moment of inertia from the neutral axis. So, kailangan natin yung maximum moment. So, next stage, meron tayong stage 2. So, this time, meron tayong cracking stage. And this before yield. And yung gamit natin na loads, these are service loads or working load. Yung service load, ito yung inassume natin na value na dadalhin of our beams or structural members. So, galing yan sa dead loads and live loads na inassume natin na dadalhin nga ng beam natin. So, this time, magkakaroon tayo ng cracks, pero kukunti pa lang. So, meron tayong crack section. And this time, yung strain of our steel is less than positive strain. Itong strain S, ito yung actual na dinadala talaga ng bakal na strain. And yung EY naman, or itong strain Y, ito yung value from the yield strength, or equivalent sa Fy over Es, or the modulus of elasticity of steel. And this time, yung stresses natin, ito yung vapor niya. So, kung i-zoom ko to guys, itong values of our strain and stress diagram, so ito yun. So, on increasing the applied load, the tensile stresses at the bottom of the beam become high enough to exceed the tensile strength at which the concrete cracks. So, syempre, pag nagkaroon na tayo ng cracks, ine-neglect na natin yung stresses in our concrete. Kaya, yung magdadala na lang yung bakal natin or the steel bars. Kaya, yung stresses dito, nineglect na dito yung stress for the concrete, and yung magdadala lang is yung Fs. Ito yung actual stress na dadali ng bakal. So, kung zoom in natin yan, ito yung drawing niya. So, as you can see, parang hindi na siya linear. So, after cracking, the tensile force is resisted mainly by the steel reinforcement. And immediately below the neutral axis, a small portion of the beam remains uncracked. These tensile stresses in the concrete offer, however, only a small contribution to the flexural strength. So, kaya nga nineglect natin kasi kukunti lang yung mabibigay niyang flexural strength in our tensile stresses. And the concrete stress distribution in the compression zone becomes non-linear. Kaya yung drawing niya parang meron siyang curvature or hindi na siya linear. So, ito naman yung behavior of our concrete at ultimate loads. This time, ito naman yung tinatawag na factor loads. So, yung service load natin, pag nag-multiply tayo ng load factors or minagnify natin yung load, ang tawag na sa kanya is ultimate loads or factor loads. So, this time, as you can see in the figure, yung beam natin is cracked na throughout its length. This is a crack section at ultimate, and as you can see, yung area natin at the compression, lumiit, and na-reach natin yung EC or ito yung 0.003. Ito yung maximum strain na dadali ng concrete natin. Yung actual strain natin nag-equal na sa yield stress or yield strain natin na EY. And this time, kitang-kita na dito yung stresses in our concrete, hindi na talaga siya linear. Meron tayong curvature, and dito naman yung actual stress naman of our steel nag-equal naman sa yield strength of our steel. So, at stage 3, at nominal strength, the neutral axis has moved farther upward as flexural cracks penetrate more and more toward the compression phase. So, yung neutral axis natin lumalamit sa top area natin, kaya lumiliit yung compression natin, compression stress, and the steel reinforcement has yielded or na-reach niya yung yield strength or yung actual na dinadala ng steel reinforcement, and the concrete stress distribution in the compression zone becomes more non-linear. So, kitang-kita sa figure na hindi na siya linear, so parabolic na siya. And below the neutral axis or NA, the concrete is cracked except for a very small zone, and at the ultimate stage, so meron tayong two types of failure can be noticed. So, if the beam is reinforced with a small amount of steel, the ductile failure will occur. Ibig sabihin, mag-fail muna yung steel natin. And in this type of failure, the steel yields and the concrete crashes after experiencing large deflections and lots of cracks. And pangalawa, if the beam naman is reinforced with a large amount of steel, so kung beam natin marami naman yung dilagay natin na bakal, yung mangyayari naman is yung brittle failure will occur. So in this case, mauuna yung mag-crash yung concrete natin at the top area or at the top compression phase. And without yielding the steel, ibig sabihin hindi pa naabot yung yield strength of our concrete and under relatively small deflection and cracks. And this is not referred mode of failure because it does not give enough warning before final collapse. Kasi, pag kukunti lang yung bakal kasi, yung failure niya, ductile failure. Ang mangyayari kasi pag ductile failure, makikita natin yung crack sa beam. Ibig sabihin, nagkikreate siya ng warning. Pero kung maraming bakal nilagay natin sa beam, tapos yung failure niya is brittle failure, itong brittle failure, yung mangyayari, mauuna mag-crack yung top face, ibig sabihin, without any warning, pwedeng sumabog yung beam natin at ultimate stage na, syempre, pag walang warning sa atin, magkakaroon tayo ng incident or accidents in our structure. So, this is not preferred by the code. Kaya dapat, yung pag magde-design tayo ng beams, dapat i-design natin yung ultimate stage failure niya, dapat ductile failure, hindi brittle failure. So ngayon, pag-usapan naman natin guys, yung equivalent rectangular compressive stress distribution or this is the compressive stress block. So as you can see in the figure, ito talaga yung actual stress niya. So yung meron tayong bending compressive stress at the top. So parabolic siya and ginawa yan na rectangular para mapadali yung pag-solve natin of our compressive force. Kasi kung mag-solve tayo ng compressive force sa actual, gagamit tayo ng calculus. Pero kung ayaw na natin ng calculus, gagawa tayong approximate value na malapit yung value niya. So ito yung equivalent rectangular block. So meron siyang height na A and meron siyang thickness na 85% of the compressive strength of concrete. So yung C, this is the compressive force na dadalhin ng top area or the compressive stress block. And yung T naman, ito yung ASFY, ito yung force, tensile force na dadalhin ng bakal natin. So the actual distribution of the compressive stress in the section has the form of rising parabola. And it is time consuming to evaluate the volume of compressive stress block kasi nga pwede pa mag-calculus tayo and kaya nga nagkaroon tayo ng equivalent rectangular stress block and this can be used without loss of accuracy. So yung C nga, this is the volume of the compressive stress block. So may 3D yan actually. So mamaya ipapakita ko anong itsura niya sa pag 3D. So kasi meron siyang thickness perpendicular sa screen nyo. Kaya yung compressive force natin is equal to the volume of this block that is 0.85 FC prime and the area which is A times B. So yung 0.85 FC prime, ito yung equivalent stress nga para maging rectangular, ginawa natin na 0.85. And yung AP and yung AB, this is the area of the concrete in compression. And sometimes, ginagamit ko din to sa solution ko kasi may mga times guys na hindi rectangular yung beam natin. Kung hindi rectangular yung ginamit natin, hindi na AB. Kasi yung AB, ginagamit lang yan for rectangular. Pero yung AC, or itong symbol na designation, ginagamit yan in any shape. So, meron din tayong notations dito sa reinforced concrete. So, ano bang ibig sabihin ng mga symbols na yan, mga letters na yan? So, yung A, so this is the depth of the rectangular compressive stress block. So, yung meron tayong actual kasi na stress, and pag kinonvert na natin sa equivalent, so magkakaroon tayo ng A na yung A is less than the value of C. Kasi yung C natin, yung smaller C natin dito is the depth of the neutral axis from the compression phase. So, itong height na yan. So, as you can see, yung A natin is less than C. And yung B is this, the width of the beam at the compression side. And yung C, this is the depth of the neutral axis nga measured from the extreme compression fibers. And letter D, this is the effective depth of the beam measured from the extreme compression fibers to the centroid of the steel area. So, yung D natin from the top of the compression fiber to the centroid of the steel bar. So, dapat papantayan sa centroid of our steel bars sa bakal natin. And yung H, this is the total depth of the beam. So usually, ginagamit yung H. So pag nagde-design tayo or analysis of the beam, yung ginagamit natin is yung D, hindi yung H. And yung EC naman, this is the strain in concrete or the strain in extreme compression fibers. So, itong strain diagram, ito yung EC. And yung ES naman, this is the strain at tension steel. So, may mga times na yung ES or ito yung strain S, yung mga times na ginagamit natin is ET or strain in T. And we have also the FC prime. Ito naman yung compressive strength of our concrete. And meron tayong FY, this is the yield strength of steel. And AS, this is the area of tension steel. And yung C naman, this is the resultant compression force in concrete na equivalent nga yan sa the volume of this block. So, that volume of the compression block. And for T naman, this is the resultant tension force in steel. That is stress times area lang. So, yung for MN naman, ito yung pagdetermine natin ng capacity of our beam. So, MN is the nominal moment strength of the section of the beam. Ito yung capacity of our beams. So, dagdagan ko lang kasi yung AS nga, hindi naman talaga yan, isa lang yan. So, for example, ito talaga yung actual na itsura niya. So, meron tayong 2 bar sa top and 3 bar sa tension or sa bottom. So, for this introduction for flexure beams, i-neglect nyo muna itong sa top kasi usually, kinukonsider mo natin dito yung behavior of our tension still at the bottom. So, ito muna yung kinukonsider natin sa introduction. So, mga next presentation ko na ipapaliwanag kung bakit ba nagkakaroon tayo ng compression steel. Kasi sa mga naunang slides kanina, yung kinukonsider natin is the concrete lang sa compressive strength. Wala pa tayong bakal sa top. Pero sa actual talaga, meron talaga dapat at least 2 na meron kakapitan yung stirrups natin. So, this is the compression steel sa top. Kung meron tayong 2 or more layers of our steel bars at the tension, itong 5, for example, itong 5 area or itong 5 bars. So, ang ginagawa natin dito is itong 5 bars, in-equate natin sa isang bar. So, ginagawa nga natin dito. And hinahanap natin yung centroid of this bars. So, kung meron tayong 5 dito, tapos meron tayong 2 layers. So, hahanapin natin yung centroid niyan na 5. And dito nakalocate yung effective depth natin from the top of our beam or from the compression fibers. So, ito yung effective depth. So, in-neglect nyo muna this time yung bakal natin sa top. Yung i-consider muna natin yung mga tensile steel bars. So, ngayon, pag-usapan natin yung flexural strength or yung MN. This is the nominal moment capacity of our beam. Using the equivalent rectangular is obtained as follows. So, gagamitin natin for C, that is 0.85 FC prime AB, and T, this is AS FY. So, this is the 3D of our compression block, and this is the 2D. So, pag-summation of forces horizontal tayo equal to 0, syempre, magkakaroon tayo ng C equals to T. So, pag in-equate natin yan, so meron tayong value of C na 0.85 FC prime AB, and for T, meron tayong AS FY. So, divide both sides by 0.85 FC prime times B. So, magkakaroon tayo ng value of A now na ASFY all over 0.85 FC prime B. Kailangan natin isaulo yan kasi ginagamit natin yan sa mga problem solving. And yung MN natin or the nominal moment capacity or strength, so equal lang yan sa force times distance. So yung T and C natin, these are coupled forces. Kung magkaiba yung direction nila, magkakreate siya ng moment na yung moment niya is pwedeng C times D minus A halves. Yung D minus A halves, this is the moment arm. And yung C, this is the force. Or pwede din sabihin natin yung moment MN, that is also equal to T times D minus A halves. Kasi nga, yung T and C are equal. So, any of the two formulas, pwede natin gamitin para makuha yung nominal moment capacity. So, finally, you can use the formula MN is equal to 0.85 FC prime AB times D minus A halves or ASFY times D minus A halves. And yung A nga natin, pag hindi natin alam, kasi hindi talaga natin alam yan, so gagamitin natin ng formula for A, that is also equal to ASFY all over 0.85 FC prime times B. So just substitute and you can solve the value of MN. So, this formula, kailangan isaulo yan kasi hindi yan given sa mga exams or even sa board exam. So, for example, guys, so basahin ko muna yung problem. Determine the nominal moment strength of the beam section. So, take FC prime is equal to 20 megapascal and yung Fy is equal to 400 megapascal. So, in the figure, meron tayong dimension of the beam na meron siyang height na 60 centimeters or that is 600 millimeters. Meron siyang effective depth na 54 centimeters or that is equal to 540 millimeters. So, yung designation natin for effective depth, that is D. And meron tayong given na 3 bars. Pag ganito yung nakita nyo guys, that is also equal to 3 diameter. Meron tayong diameter na 25 millimeters. And meron din tayong width na 35 centimeters or that is 350 millimeters. So ngayon, para mapasimple natin yung pag-solve, so first, in-neglect muna natin yung compression steel natin, itong dalawa. Tapos, yung stirrups, just neglect muna natin yan. Yung itong 3 bar, gagawin natin na isa. So, i-compute natin na AS na yan. Mag-assume tayo ng location of our neutral axis, na yung location niya from the compression phase, that is C. And meron tayong equivalent stress block na yung height niya is A. So, for the solution, yung formula natin, meron tayong dalawa. So, you can use any of the two. Pwedeng ito or pwedeng ito. So yung problema lang natin dito sa formula, wala tayo ng value of our A. Na-derive natin yung value of A kanina, na ito yung formula niya. So kailangan natin yung value of AS or the area of the seal kasi yung Fy given, yung Fc prime given, and yung B given din. So yung S natin, that is also equal to 3 times the area of the bars, which is 5d squared over 4. And yung diameter of the bar, that is 25 millimeters. So you can pause the video and calculate this value. And that is equal to 1,472.621556 square millimeters. So, hindi ako guys nag-round off para accurate tayo. So, pwede nyo guys i-pause yung video and i-check kung tama ba yung pagka-calculate ni Engineer Jack. Ngayon, substitute the value. So, yung AS natin, that is 1,472.621556 square millimeters. Yung Fy, that is 400 megapascal, or yung 1 megapascal natin, that is also equal to Newton per square millimeters. And all over 0.85 times yung Fc prime natin, that is 20 megapascal or 20 Newton per square millimeters. And yung B natin or the width of the beam, that is 350 millimeters. So, cancel yung square millimeters dito and magka-cancel din yung newtons. Tapos, magka-cancel din yung isang millimeters. So, dito, magiging isa na lang. And yung millimeters dito, iaangat natin. Kaya yung unit natin for value of A, dapat naka-millimeters din. So, pwede nyo guys i-pause yung video and i-calculate yung value of A. So, yung A natin, that is 98.9997685 millimeters. Halos 99 millimeters na. So, now, any of the two formula, pwede natin guys ma-solve yung nominal moment capacity niya or nominal moment strength. Pwede natin gamitin yung 0.85 Fc prime AB times D minus A halves. So, substitute the value. So, 0.85 times 20 Newton per square millimeters times yung A natin, that is 99 millimeters, times yung B, 350 millimeters, and times yung D natin or the effective depth, that is 540 millimeters, minus A halves or 99 millimeters all over 2. So, pwede nyo guys ulit i-pause yung video and i-calculate. And that is equal to 288,929,025 newtons millimeter. And i-convert natin sa kilonewton meter, so mag-divide tayo ng 1 million. So, yung MN now is 288.929 kilonewton meter. And this is the answer for this example problem. So, as you can see, marami talaga yung formula na isasaulo natin dito sa reinforced concrete. And hindi pa yan. So, abangan nyo pa yung part 2, part 3, and part 4 of our flexure in beams. So, marami pa tayong i-consider dito, especially sa analysis and design. So, ito, introduction pa lang of our reinforced concrete in our flexure of beams. So, that's it. Thank you very much and have a good day.